break and give everyone time to catch up with new contributions. And we will listen to some external speakers to learn from other industries how they're developing and deploying their autonomous systems in safety critical applications. So our first guest speaker is Boris Ivanovic from NVIDIA. He is a senior research scientist in autonomous vehicles group, has done his PhD with Marco Pavone, who is now directing this big group at NVIDIA. So we decided to select our speakers from academia and industry and alternate them. And people from academia are the ones who have tangible impact on different industrial developments. And Marco was a former collaborator from our NSF NRI project. We decided just to reach out to him as first. Thank you very much, Boris, for giving us an hour of your time this morning. Just share your screen and go ahead. Thank you.
Thank you very much. Yeah, let me share this and we'll get into it. So yeah, hi everyone. Thank you very much for the opportunity. My name is Boris. I'm a senior research scientist and manager within the Autonomous Vehicles Research Group here at NVIDIA. And today I'm going to be talking about how foundation models such as large language models and vision language models, which you may have heard about, or at least in popular news, provide a key opportunity to rethink how we can develop autonomous systems, and in particular autonomous vehicles, at least which we're concerned with. So currently, autonomous vehicle technology is actually already quite reliable in specific operational design domains. We have very advanced ADAS systems right now that are being productized as we speak, and remarkable progress is being made by Waymo and other startups that are trying to now deploy self-driving cars as a service. Now, this has been powered by the judicious incorporation of specialist machine learning models within the AV stack. However, these systems still miss the mark when they're exposed to really the long tail of everything, of the distribution of everything that we can possibly see out there in the real world. And this might include new deployment domains or optical illusions, or even just other strange scenarios that require some higher level semantic reasoning for generalization. So the real core question here is, how can we kind of enable this, let's say, generalization capability? And one thing that we've been doing in the group is taking a look at how, for example, humans are able to naturally do this. And the reason that humans can do this is that we have really a lifetime of experiences beyond just driving, which enables a really strong contextual and semantic understanding capability to reason about long tail events. So analogously, the hypothesis that we have here is that foundation models, which have been trained on many lifetimes of very diverse data, both in driving and non-driving domains, provide an opportunity to bring this outside information into the task of driving and thereby equip next generation AV stacks with the understanding and reasoning capabilities needed to navigate that long tail. At least this is the hypothesis. So the core question is, how can we actually access this generalist experience for AV applications? And the answer is in multiple ways. So as I'll discuss in the rest of the talk, through their long-tail generalization capabilities, foundation models can empower several aspects of the AV design and development problem, from improving offline development processes like auto-labeling or simulation, all the way to improving on-vehicle driving performance, for example, by enabling more performant end-to-end driving stacks or by enhancing driving assistance systems. So in other words, they really provide the capability to empower the full AV program. And the convergence of all these advancements is really, in my opinion, what might lead to the next level of vehicle autonomy. Now, of course, safety is paramount, and a common concern is that foundation models might not be safety fielded in a safety critical system such as an AV. Now, unfortunately, in this talk, I won't have as much time to go over some of our latest results in this space, but I'll provide some links at the end to our recent work, which actually dive into how foundation models can be used to not just improve safety, but also how we can enact guardrails around model outputs. So in the rest of the talk, I'll first start by discussing some key considerations for how to build foundation models for autonomous systems. And then I'll discuss how they can be used in a variety of ways as part of an AV program. So to make sure we're all on the same page, I'm just going to define some key terminology using a running example of multimodal large language models. So these models indeed represent a pretty prominent example in their own right for AV applications, as they enable us not to just process only text, but a rich array of data types like video, LiDAR, and various sensor modalities, which you very commonly see in the autonomous driving domain. So the way that they work is typically they will first encode these kinds of diverse inputs into a unified latent embedding space, and they'll here use a neural network that basically extracts those features from raw data. These latent embeddings are then referred to as tokens, which can represent any information from semantic units of language and image patch embeddings to vehicle states and actions. And these tokens are then processed by some sort of backbone neural network to generate output tokens. And in this running example, a backbone here is typically a large language model in and of itself, which autoregressively can generate output tokens. Then we finally have task-specific decoders that take those output tokens and actually decode back the information that we are interested in. For example, trajectories or other kinds of outputs that are relevant for the tasks we have at hand. So with this kind of concept in mind, some of the core choices that underpin how to build an AV foundation model are data, the actual model itself, and then the kinds of tasks that you train it on. So, as I mentioned in data, there's kind of a really wide range that can be used, like, for example, internet scale, just general images and text that you might find on the internet, to more specific task data like videos of driving or LiDAR or, even just vectorized information like maps or trajectories that you might have collected from, your AV driving around. On the model front, there's kind of a few key architectures that have emerged as really promising choices, and I'm going to show some examples of these. And then for training, we typically split this into two kinds of training regimes. The first is self-supervised, which is really to just enable learning very general capabilities, like ideally common sense reasoning and generalization across different domains. And then we have supervised fine-tuning, which is, once you have a pre-trained model, you can now try and tune that model for your specific use case. Like if you want to do, output trajectories or detect objects in an environment or track them across time, etc. So I'm going to talk about some examples of recent models and some of the choices they've made here to illustrate it, but these are kind of the typical axes you have at hand. So one prominent example, like I mentioned earlier, are multimodal large language models. So these are exemplified by, some very recent releases like Gemini from Google, ChatGPT from OpenAI, and then other research models like Lava or some works from Google like RT2 and Palm-E. And the choices they make here is typically their backbone is an autoregressive transformer. They're typically encoding multiple different kinds of data, and they use many, unsupervised pre-training and supervised fine-tuning tasks for their specific, tasks at hand, which could just be answering questions, or it could be, all the way to robotic tasks like moving things around in an environment. And one thing that I want to mention is, as an example of the kinds of long-tail reasoning capabilities that can stem from, like a general pre-training and fine-tuning training paradigm, is that you really get some long-tail reasoning capabilities. So this is an example from one of our recent works, LADA, which leverages LLMs to help a human driver reason about what to do when faced with an anomalous situation. So effectively, it acts like a co-pilot. So in the video here, you can see, the car is driving down some countryside road, and there's some horses on the road. And here it's, actually able to make the suggestion for the driver to slow down, keep to the right side, and pass the horses cautiously to avoid startling them, which, all of this seems reasonable, but it's really great to see that even in a rare event like this has never been included in the training data of the original foundation model, and yet it's still able to reason about it. Now, Another prominent example that you might have heard about recently in the news are video generation models, sorry. And these models are exemplified by works like Sora from OpenAI, Gaia from Wave, and other open sourced or commercial models like Stable Diffusion and DALL-E, where they're typically trained primarily to generate videos. So they kind of typically work primarily in the visual regime, and they use a hybrid backbone which combines, transformers and diffusion models, which are, I would say very popular choices nowadays for such a neural network architecture to generate images and videos. And I want to show an example of a work being done right now at NVIDIA to actually scale up this video generation approach and actually make it more directly useful for autonomous driving. So beyond just, generating videos, something that we're also very excited to do is to incorporate other kinds of conditional information like, sensor calibration information or text descriptions of what we want to be generated, or, the ego vehicle's next action in the scenario to maybe generate, again, some kind of conditional video based on the movement of the ego vehicle. And some recent results, which are quite exciting, are actually showing that we can not just incorporate all of that information, but actually learn about geometric consistency across multiple cameras. So I'll show these videos again. But basically what you can see here is that this, video generation model that we've been training is able to not just, generate realistic environments that are kind of typical, let's say, of the area here in California, in the Bay Area, but it also has learned to, ensure that if a car appears on the left and it passes some, kind of threshold for where it can be included in multiple cameras, that it should actually appear also in the center, in the central camera, as you can see with this black vehicle here. So just to show an example of what we've been currently working on. But of course, the jury is still out on kind of what's the best model here that should be used for driving tasks, or should be used on vehicle or off vehicle, or et cetera. But at least, what we're pursuing within the company is multiple approaches in order to both learn about, the benefits of both of them, but also in order to actually eventually unify them. For example, by having both models share the exact same latent space. So you can have now a model that has very strong video generation capabilities, but also the ability to encode many types of data modalities and output many types of data modalities by leveraging, for example, by sharing the same kinds of decoders and encoders across both models. So, keeping these in mind, I want to come back to the central question that I posed at the beginning, which is how can we actually use these kinds of models for real world AV program development? And as I mentioned before, there are kind of two core areas where we can bring them in. The first are in offline processes like auto labeling or simulation, and then in the on-vehicle stack, in the development of novel end-to-end architectures, or as an in-cabin assistance, like I showed just a bit ago. So I'll discuss some recent results for each of these applications, starting with offline processes. So a key problem in AV and really more generally in robotics is finding an effective world representation. They summarize our knowledge of the environment and can be used to create and curate new data, simulate what might happen, and of course, enable downstream AV tasks of interest. Now, as I mentioned before, foundation models really have this powerful capability, like video foundation models have this very powerful capability to actually reason and generate, plausible predictions of what might happen in the world. And, we're definitely excited about working on using this kind of a representation as a world model, but that's still, a little bit, let's say, maybe a few years out. And so, another complementary route and perhaps more immediate to using these powerful models is to actually imbue existing world representations such as NeRFs, occupancy maps, voxels, Gaussian splatting, etc., with internet scale priors. And really bring that strong semantic understanding capability that we want from foundation models into these existing representations. And I'll show an example of what this looks like and what this enables. So the first, sample here, let me see. Where is my mouse? Okay, just a second. I think my computer froze a little bit here. So let me see if I can bring it back. I have some videos coming up next, and so that's why I don't think it liked that very much. But let me see if I can resurrect things here. While I'm doing this, if there's any questions from the previous section, I'd be happy to take them. I don't think I have to drop the call. I just have to try and restart PowerPoint here. Okay, good. And then we are back. Sorry, everyone, about that. Okay, we should be back very soon. Okay. Let me share this and then bring this back. Okay. Okay, sorry about that, everyone, but at least we're back here. So with respect to imbuing existing world representations, the problem domain that we started looking at is in dynamic driving scene reconstruction and representation, which is a really core underlying task for simulation, but also auto-labeling of real-world environments. And in one of our recent works, this is a paper accepted to ICLR, we've developed a model called EmRNeRF, which enables us to jointly model static and dynamic components of the scene. So in this video, what you're able to see is how we can actually naturally segment a video into its components, static, dynamic, and flow components. And what's very powerful about this approach is that all of this is achieved solely via self-supervision. There are no ground truth labeling or any annotations actually used to train this model. It's purely learned from self-supervision. And that the way that the model works is it segments the, it decomposes the world into three core components, each of which are neural fields or NeRFs. So they are a static field, which contains stationary elements of the scene, a dynamic field, which contains moving elements, and then a flow field, which models correspondences between dynamic elements across time. So as I said, this decomposition is learned entirely from self-supervision. And the key technical aspect that really enables some of the very strong performance that you see here is an emergent scene flow estimation capability that greatly augments the modeling of dynamic objects. Essentially, what we're doing is we force the dynamic field here, which is the second last row, to use features from both the next frame and previous frame, which are aggregated by the flow field. So we're kind of forcing it to have temporal smoothness. If you didn't have that flow field, what we observed was actually those dynamic decompositions are very flickery because your dynamic field just learns to memorize every time step individually without having consistency across time. So it's actually this mutual reinforcement between the two fields that ultimately yields this very crisp distinction between static and dynamic objects. Now, one thing that's actually very powerful about this is, these results that we obtained were already great, in terms of this semantic decomposition. However, the model can't tell you if this is a car or a pedestrian or a bus. All it can say is just, it moves. And so, this already enables many tasks like log replay and novel view synthesis. But if we're interested, as we always are, in the semantics of the scene to actually understand what's going on, we need to bring in some other kind of understanding for semantic information. And this is where we can actually leverage the exact same training paradigm that we're using, which is to simply render the scenario and generate RGBs and then compare that to the ground truth RGBs, and use that to not just render RGB data like color or pixels, but also foundation model semantic features, so that the model is now able to distill not just the RGBs, but also semantic information from other models that were pre-trained by someone else elsewhere. And what this enables is some really powerful capabilities for auto labeling and querying for concepts. And the examples I'm showing on the bottom here are, we basically distilled features from CLIP, which is a model that combines text and images. And what we've been able to do is then literally type in queries for example, a car, and then you can see all cars on the top right video. All cars in the scene are now highlighted. And if we actually continue this process, we can completely semantically segment the image without any ground truth labels required, which is really, so out of hand, we already get a really powerful tool for auto labeling. And, going one step further, what such a world representation is really useful for is that because NeRFs themselves have a 3D or 4D model of the world, it means that they can actually maintain geometric accuracy if we, ask them to render other kinds of sensors like LiDAR. So here on the right, I'm showing, the ground truth is in gray on the left here, kind of the LiDAR traces from the point cloud from the actual environment. And then on the right, I'm showing a purely simulated, purely, feed forward point cloud that's generated from this MNeRF's understanding of the world. And we can see that it's actually very well reproduces the ground truth. On the left, I'm showing, on top is the original camera log from the data, and then on the bottom is the rendered sensor data. And you can see it's, at least in this kind of a resolution, it's extremely hard to see any differences. It's a near one-to-one match. And this is really powerful because it enables high-fidelity sensor simulation, which we're quite excited about. However, one caveat is that the agents that you're seeing here are purely being replayed. And so to really fully close the loop on simulation, we need traffic models that can actually control the behaviors of these agents in ways that are different than what just happened in the replay environment. So, accordingly, the group has also conducted a lot of research in traffic simulation, and we've been pushing the state of the art in terms of realism, diversity, and controllability of simulations. And we're really now in a position to produce, while we're in a position to produce high fidelity traffic behaviors, actually creating such simulations typically requires a lot of manual work behind the scenes in terms of, well, one is just tuning parameters of these kinds of models, but also generating the map or generating the urban layout around which you want to place these scenarios. So there's still a lot of artists and assets that are involved in creating such simulations. And so another direction that the group has been pursuing in actually remedying this kind of manual labor is using foundation models to provide a very natural interface to generate from scratch simulation scenarios, including even maps. So specifically,
may I ask a question?
Yes. Yeah, go for it.
I would say it's a fascinating, wonderful presentation. So my question is about the self-supervision. Is that in the sense of like a reward function in reinforcement learning, or a complete different architecture?
Yeah, so self-supervision here is referring to the fact that you can use, it's a bit of an umbrella term, but at least when I'm mentioning it here, I'm basically saying that all the learning signal that you need comes from either what you were given as input or what you have as output, with no additional annotations required. So it's kind of you're able to supervise yourself, so to speak. And the way that we do this, you can think of an example like if you're auto-encoding an image, you take the image that was given an input, image that you generate as output, and then try and match them, for example, with a pixel-wise loss or something like that. That's like one example.
Yeah, I get the example, but usually to learn, you want to start with something you already know, and also, yeah, this close, modify what you learn, or you need a complete new idea. Well, at least that's what human learning does. So most of us knows reinforcement learning. They can give a new game, right? You never seen AlphaZero set. They will figure out how to play it and do amazing policies. So my question is, from the architecture perspective or structure perspective, is supervised self-supervision plays a role similar to the reward function, let's say in AlphaZero or in some other reinforcement learning? Or they say, no, it's fundamental, it's orthogonal, has nothing to do with it, or it's similar? That's my question.
Yeah, that's a good question. I actually think it is similar. And the reason I say it's similar is that typically I mean, they're orthogonal in the sense that, like, maybe they come from different fields, and so you could see them as orthogonal, but actually I think conceptually there's a similar idea. And here the similar idea is that with self-supervised learning, and I think similar to reinforcement learning, you're able to use a vast, diverse amount of, be it scenarios or data, to basically learn some kind of strong internal general representation, which is, for example, what AlphaZero is doing as well. And then you're able to use this to try and generalize to, as you said, either new games, new scenarios, new sensor types, or whatever. So I think there is a parallel here. It's not exactly the same, of course, but I think that there is a parallel here in that that self-supervised learning.
Thanks. Yeah. So what are the real difference there? So we know there's similarities, but it's the difference makes the difference.
Yeah. So
what
the big
is the difference conceptually or mechanically?
Yeah, I would say basically the big difference is, so RL, you're typically concerned with something that looks like some kind of Bellman backup update to an agent behaving in some environment, or at least that's kind of the, let's call it the typical regime that's being operated there. Whereas self-supervised learning is kind of just a big umbrella term for any kinds of loss functions that you can backpropagate that are based on reproducing the input that you get. In reinforcement learning, you don't typically reproduce the exact input that you're getting. Like typically you take an image as input and then you produce an action as output. Whereas in self-supervised learning, it'll be like you take an image as input, but then generate an image as an output.
And then you try to see the difference. So what is here is that you introduce a feedback into it. Is that correct?
Yeah, so for RL, exactly. You're going to try and match like the distribution of maybe the actions that some expert took as one example. And then in self-supervised learning, you'll try and match, for example, the distribution of, rather than something and an expert gives you, it's just the distribution of data that you were given.
So you are doing some sort of maximum likelihood conceptually. So in the latent space.
Exactly.
So thank you for helping me understand, because this is really new, fascinating. It's a dimension I didn't look into, but I did look at the other things. So now, I have similarity. So essentially, you put a feedback loop, and the purpose of feedback loop in the self-supervising is you try to calibrate the generate data with the actual data. So essentially, introduce a feedback mechanisms to learn. Is that correct or is false?
No, I think that's, I think that's a pretty reasonable understanding of it. It's very similar to, general learning paradigms where you're, exactly as you said, you're bringing this feedback mechanism to understand, what you need to change in your model and then make your gradient updates to that. Yep.
Okay, so it follows that. Now, there's another aspect is actually solve a lot of problems. I know some tough problems known as spurious correlations. So in some sense, you do the classical mathematics. You take this high dimensional thing and cast in the lower dimension, say, okay, it's moving, not moving, or something. So one question I will have is, if I see a tree sway in the wind with big wind, I see a car moving slowly. Now, if you measure the pixel movements, the tree actually has more movements than the vehicle. So which one is moving object, tree or the car? For humans, say, hey, come on, So it cannot sort of do a simple convergence on the loss function. Say how many pixels, say the branch is swaying, and this car just crawling slowly in this way. So the question is, how can you distinguish the two if one cannot brute force it? Say, okay, I look at the movement of the pixel or trace it. I couldn't do it. It must be something, or actually it remains to be a challenge to be solved.
Yeah, I would say this is actually a pretty open challenge, or at least you need to bring in semantic information. So like the model that I showed in the just a few slides ago, where it had this ability to decompose the world and all that, it cannot tell you, is the moving object the tree or the car? It will just say both are moving.
That's exactly. Now, what you said, something is very important, is the ability of a human is they can reason in a higher dimension, such that what they know, so it's quote unquote, that's the famous common sense question.
Yep.
So because it's not hard for the current AI to recognize as a car or a tree. In fact, it's pretty easy. So if you infuse this into it, then the question is it a swaying tree or a car? Become much easier in the feedback and convergence. So the question is, why not?
Yeah, no, there's basically what we've been doing to actually help provide this capability is, so beyond just that model, which, like I said, couldn't tell you about the semantics, that's when we bring in these external features from other models, and they're actually able to, so you can see here on the bottom right, now it's not just like, now each object is actually, we kind of know what it is. And so if we see, let's say, a tree swaying or something like that, we can say, okay, this is just a tree swaying, because now we actually understand what it is. So it's exactly this, the model itself can't do it, but that's when we bring in other knowledge, which is, where these kind of foundation model features can really help. Of course, we're still improving these capabilities. They're not going to be perfect, but that's kind of the hypothesis, that we can bring in this kind of higher level reasoning.
So if you don't mind me to go to the logical ending, yes.
Sure.
When you bring this, you want to bring it in a single latent space, or you want to bring it sort of as neural nets, like a human brain. Now we smell, left hand, right hand, motion, you see the brain all separate, or for all senses. And then you have a hierarchy of reasoning, actually eventually go to cortex. And then at that is very sort of performing a symbolic logic. So the question is, when we bring in those things and managing the complexity, do you favor a neural net approach? That would make it easier to explain and debug too, I suppose. So in some sense, we bring in the concept of modularity back to there. Is that make sense to you, or you think it's completely go off the road?
No, I think this is actually what we're trying to enable here is you maybe if you were just chasing, let's say, pure performance, maybe you might just, have, throw everything into this same latent space, have it be completely uninterpretable, but performantly it'll be very, it'll be excellent, but you have no idea what's going on internally. So, a lot of our other research, which I actually have examples of in the rest of the slides.
I know you don't, because you take the scenery and try to decompose it, say moving, not moving, and something. Yep. So you take a sort of a decomposition approach. Oh, by the way, do you need to supervise the decomposition, or you give the human eye?
No, not at all.
So how do you tell it make it into 3 categories? You can make it into red car or green thing, or tall or short. He can make arbitrary categorization. So but you want the categorization consistent with what you want, moving and not moving, say not different color or size or shape.
Yeah, so we chose, we basically chose this decomposition, not so much because it's something that we actually could choose easily. It's more, we actually chose which dimensions these 3 components are responsible for modeling. When I say dimensions here, for the static field, we just said model 3D static components. Actually, I should just say we just asked it to model anything that's 3D, just XYZ position, and placement of things. And then in the dynamic and flow field, we said model 4D things, so 3D position and time. And that's actually where that decomposition comes out.
Okay, so you give them very high-level structure information.
Exactly.
You may ask them, say, have a velocity field. So that will embed into the loss function of the self-supervision. Do I get it right?
Yeah. And so the loss function is literally just reconstructing. So you would render an image from these by combining these, and then you simply compare the image that you render with the ground truth image, and you just try and make them the same. You basically you have pixel-wise losses, like the Euclidean distance between pixels, for example.
Thank you so much helping me to understand your work. It's amazing work.
Of course, thank you. So I was just about to talk about some of our latest research on bringing some of these similar capabilities to ease the interface with which you can create simulations. And I'm going to first show the capabilities, and then I'll talk about how the model actually works internally. But something that we've been able to do recently is enable transforming text to simulation. So one example of this is if you have some kind of initial scenario, maybe from some logged data that you have, you can edit it by providing some prompts like these examples here. But you also don't need to start from an initial scenario. Something that we've also been doing is just going directly from text to simulation. And what I'm showing here on the bottom is these prompts that I've taken, like this vehicle 1, vehicle 2 descriptions, are actually from real-world crash reports from the National Highway Transportation Safety Administration. They have a database of crash reports, and we've been able to take those reports, generate not just the environment, but also the trajectories of agents within that scenario, and recreate these crashes in a simulated environment. Which is, as you can imagine, quite a powerful capability especially for verification validation of an autonomous driving system. And the way that this model works, and where we actually bring in this foundation model, this large language model capability, is kind of a 3-stage process. We start with a prompt of interest, and then we bring that, we use an LLM to process that into a structured representation, which is now, both machine and even human interpretable, or at least because we kind of choose these different structures. We then use that structured representation to retrieve, a map from a kind of a database of cropped maps, and then place agents on that map and generate their initial trajectories. And so this is kind of that 3-stage process, which I'm visualizing here. I saw that there was a question in the audience.
Oh yeah, sorry to interrupt. Boris, can we move to the previous slide?
Yeah,
I have
of course.
a question on that.
Here, let me do that.
Yeah, I think it's a very interesting that we can generate some, like, for example, like failure scenarios by text. But my concern is that, like, probably the all like scenarios are very high dimensional. So even if we can generate some, scenarios like failure scenarios, that would not cover all the scenarios. Like we don't know like how high, how can I say that, like how complex the dimensions are. So do you have any idea on that?
Yeah, this is a great point. Yeah, you're right. And I think that's actually still kind of an open problem even right now, is really understanding the full gamut of actual realistic scenarios that can happen. What we're mainly doing here is, previously it was very difficult to produce these kinds of rare events, or at least you had to have like an artist reading themselves like crash reports and then recreating it by hand. So here we're kind of trying to expand that capability and make it a little bit more seamless and automatic. But you're right, this doesn't answer the question fully, as in like it doesn't completely solve the problem, because as you said, still, and I would say, yeah, it's still an open problem. We're definitely working on it, but I would say it's this is kind of a step towards that eventual goal.
Maybe you can call all the like like incidents reports from the internet. Maybe you can generate all the scenarios from the internet. Then maybe better. Yeah. Okay. Thank you for the answer.
Yeah, it's definitely better, but even then, generating full coverage is still elusive.
Thanks for your answer.
Thank you. So combining, so just to basically wrap up this section here, and I basically want to bring it back to, so I showed sensor simulation and how we might model the world and use it to re-render it. I've also shown some examples of traffic simulation, but if you think about it, for like real, to actually model the, to use something like this in simulation, we actually want both. We want to simulate sensors and the agents moving within them. And so something that I'm really excited to show is some, really late-breaking results from our group is, so on the top, I'm showing, this is just a scenario collected from data. So simply, you have a car passing through an intersection, it kind of stops at the stop sign and then moves forward. Okay, great. Nothing really too crazy here. And, along this line of rendering a little bit rare scenarios, I'm actually going to show a modified version of that same scenario, except that car that passes through does something a little bit different. And so here on the bottom, it actually speeds through the four-way intersection. So it's kind of, we've been able to change how the agent moves, render it and visualize it in actually a realistic manner, and be able to use this to now reason about what would the AV stack do in this scenario with, real sensor or like realistic sensor input. So this is really, we're quite excited about this because this is, quite a strong step towards the
Boris, this is Louis again. Just a short question. I saw this. Does the notion about stop sign are ever being recognized and used?
That's the motion. What?
Does the machine sort of have a token capture, say, hey, man, there's a stop sign? Or that actually completely buried into the latent space is all on its own. So which is which? Because you kind of favor.
It's not explicit.
It's not explicit.
Correct.
If you may express, because stop sign recognition is relatively easy. So if you do the explicit and inexplicit approach, which one you prefer in terms of long-term research towards more understandable and structured machine learning, or you want to bury it in the latent space? So my question actually is very simple. If something can be bring out from the latent space, would you do it? I know something you couldn't, but will you try to get all the things in the latent space, but we can get it out and then correlate with a human model? Would you do that? Or you say, I don't care?
The question that you're asking here is a little bit different than what I'm actually showing here, where it's not, so what I'm rendering above and below are simply this, the ego vehicle that's driving here, all it's doing is just, it's being driven by a human collecting data. And what we're doing is modifying how other agents in the scene drive, kind of presenting a counterfactual scenario for simulation use, or basically for evaluation use. So here, there's no even reasoning about stop signs or anything like that. We're simply directly, creating a rare event by, as if another vehicle, for example, driven by a human, completely ignored the stop sign and just, drove quickly through the intersection. So at least from what I'm showing here, that's kind of there's no like, let's say, explicit reasoning about stop signs or anything like that. It's more just showing an example of a scenario where another car doesn't.
Okay.
Stop
so
signs.
You are not trying to say this is a driving unsafely or illegally.
I'm just showing exactly as you said. I'm just showing a counterfactual but quite rare event where a car completely ignores the stop sign. And then yes, I'm not ascribing a value of, is this, this is numerically this number amount of safety or not. I'm more just showing that example.
Okay, thank you.
Yeah. So I actually think this is a good point for me to, I'll kind of go towards the conclusion. So the overall, I think with all these capabilities, and we have some more examples on how we can augment kind of the on-vehicle stack, but in the interest of time, in something that we're really excited about, as I said, the initial hypothesis that we had is that we can bring forward these kinds of really broad semantic generalization capabilities from foundation models and use them to empower AV program, offline and online use cases. And with some of these examples that we've seen where we can, really bolster simulation, really bolster world representation and understanding, we're quite excited about this potential. I've talked about some models that are, prominent examples of foundation models for AV, like specifically these video generation ones or multimodal large language models. And the way that we think about it, to also answer a kind of an earlier question, the way that we're thinking about using these models for AV development is not necessarily to like wholesale replace existing components. I mean, I'm sure it could replace existing components, but actually we're more excited about the capability to improve existing components by bringing in such a powerful source of semantic information, like a model that was trained on the internet. And so in particular, we're really excited about the ability for foundational models to make closed loop simulation, evaluation, and training really much more arguably within reach than they were maybe a year or even 2 years ago. And final thing that I'll say here is that it's important to note that these kinds of models, they're not just black magic. Yes, they have implicit latent spaces. Yes, they're not interpretable, but there do exist strategies to confidently deploy them, and there do exist strategies to actually use them to improve the safety of autonomous vehicles. Like I said, by enacting guardrails around their outputs, but also using them as, for example, semantic runtime monitors or anomaly detectors or out-of-distribution detectors. So with that, I want to thank you all for your time and attention and open it up to any questions.
Hi, Boris. I have a question. I'm Vasu Salapaka. Very nice presentation. Now I understand that you're developing all these simulation models. I have come a little bit late to the talk, so maybe you might have answered this before. So the question is, now when you are creating these rare events, and which would be, I think, more useful for actually evaluation and doing contingent events kind of stuff. And rare events are actually rare. Then how do you qualify whether these rare events are natural enough, or maybe you will learn something wrong because there may be some bias in the way you're creating these rare events?
Yeah, this is a great question. So I think if we were just doing, generation from scratch with no grounding, I think you're exactly correct. I would also be worried about having, some kind of bias that's introduced by the model. So our hope is that by grounding the generation of these kinds of scenarios in, let's say, textual descriptions of real-world crash scenarios, then we have like a tether to realism by basically what was observed before. Now, if we, try and sever that tether, that I would say is an open problem. I think the jury's still out on how you could do this without introducing bias. But I think, at least for now, there's still a treasure trove of data in, like, for example, police reports, insurance reports, governmental collected crash reports that, we're focusing on leveraging those first. And then, maybe then we'll have to see, once we exhaust those, which who knows how many years that will be from now, once we exhaust those, then maybe we will have to revisit that question of how you can generate without trying to introduce some bias. But that's a very difficult problem, I would say.
I think here there may be a concept of, you can do a lot of maybe even impossible stuff and go for most, most conservative approach. So there can be a whole gradation of being how conservative you are in your solutions, and design for that. That can be another way to think about it, I guess.
Yeah, could be. You could also think of it as anchored from the perspective of the AV stack, or like the autonomy stack that you're developing. What kinds of scenarios are going to test your stack the most? Maybe it doesn't care about certain things, or maybe some kinds of crashes are also, it doesn't really matter. So that, you can also make it relevant for your particular use case if you know something, that you can bring in some external information that yourself.
Yeah. Okay.
Thank you. Boris, this is Lloyd again. I work on safety. That's most of my career. So in terms of AI safety, more recent thing. So what you talk about sort of fundamentally is, it seems you prevent, you try to bypass a sort of a whole big problem, baffles the AI community for a very, very long time, is the typical approach to solve, because all rare event, accident event are long tail event, as you said. So a lot of people try to solve it, try to augment the data, but it's not easy. You will introduce bias. So what you say is the LLM itself, in some sense, looking at the world, accumulating knowledge, probably more than a single human can ever able to accumulate. So in the latent space of LLM, those information exist and in fact can bypass the data imbalance, the contextual information from LLM actually is the compensation for the data imbalance problem. Do I understand you correctly? So
I think that's about, yeah, I would say that's close to close to correct. I would say the only thing I would add is that here we're not asking the LLM to, let's say, regurgitate from memory a rare event. We are asking it to basically transform an already existing description of a rare event into a structured representation that then the rest, the later on neural networks can use to do, for example, retrieving a map or placing agents on that map. But I would say yes, we're basically leveraging...
What you said is remarkably like how human brain works. Say the smell, the motion, you want to put your hand around obstacle. That's sort of actually, I really want to talk to you about the guardrail and safety thing, because that's what I'm working on. This is Louis. How can I contact you or can talk to you?
Yeah, my email, I think, was, you know what, I just brought it down. Let me reshare. My email is here in the
Louis, I can share the email. You can certainly, I can put you in touch.
And in fact, we try to do a safety landing. Naira's leadership is for a, for this ULI program. And what we actually particularly working on is a visual guided safety learning in very bad weather, like a snowstorm or something. So if we could talk to you and learn from you, I would greatly appreciate.
Yeah, absolutely. And like I said, we actually have, a lot of our work on safety is now actually, I mean, it's not just work that we've done or it's ongoing, but it's actually growing within our group. We just made some key hires and we're actually expanding that direction. So yeah, very excited to talk about that as well.
Thank you.
Any other questions?
If no other questions, we can maybe close the Teams on time. Thank you very much, Boris, and I will follow up with an email to make the connection with Luisa and our perception group within our NASA ULI. This was very interesting. I hope you found the questions and discussions beneficial for you as well.
I did very much. Yeah, thank you very much for organizing this, and thank you all very much for attending and for your questions.
And may I ask you to share your slides so we posted on the website the slides and the recording of this so that other people who couldn't attend today, like NASA and Boeing people emailed me that they had a meeting, they couldn't join. So they're looking forward to the recording.
Yep, both of that is perfectly fine. And yeah, let me know if you want the just PDFs or even the raw PowerPoint. It's just a bit big with these videos.
I mean, whatever you feel you can share, it's great.
Both.
You want both? Okay.
Sure.
Okay.
I can definitely do that.
Yeah.
Thank you, Boris. Thank you, and pass my regards to Marco. Thank you for arranging it. So I guess there are no more questions, and we can close the Teams now.
Sounds good.
Thank you.
Thank you very much.
Bye.
Bye-bye.
Bye-bye. Thank you.